Welcome to this afternoon session. Have a seat. And we are pleased to have our first keynote speaker, Marie-Colette Van Lieshout. And Radu Stojka is going to come and give a few words to present Marie-Colette. Unfortunately, she wasn't able to come, but we have a video and we will play the video right after.
Okay, thank you very much, Guillaume. Hello, everybody. My name is Radu Stojka, and I'm professor in mathematics, probability and statistics at the University of Lorraine. I'm working on pattern detection and characterization in spatio-temporal data. And it's a great honor to be in front of you and present Marie-Colette Van Lieshout. Marie-Colette was my postdoc advisor during 2 years, 2001 and 2002. That I was able to do something good and interesting was mainly due to her patience, her kindness, and her constant efforts to help me to make progress. Marie-Colette is a wonderful teacher and an extraordinary researcher. Her work in image analysis has contributed to shifting the modeling paradigm from pixels to objects. She has major contributions in stochastic geometry, Markov point processes, and spatial statistics. Her 2 books, Markov point processes and their applications, and Introduction to the Theory of Spatial Statistics, are complete, concise, precise, and elegant pieces of mathematical work. In simple words, beautiful. Beauty, elegancy, and intellectual courage are the words that characterize the entire academic work of Marie-Colette. Please give a warm welcome to Professor Marie-Colette Van Lieshout from CWI Amsterdam, and please join us in the follow-up session of Random Patterns. Thank you very much.
Welcome everybody to my presentation, and a special hello to Radu Stojka. Thank you for having me. Today I'm going to tell you a little bit about parametric and non-parametric monitoring of induced seismicity in a gas field in Groningen in the Netherlands. This is a large gas field. It was detected in 1959 in farmland near Groningen. It was at the time of discovery the largest gas field in Groningen, in the entire Europe. The size is about 900 square kilometer, and there is a recoverable gas volume of around 3,000 BCM is billiard cube meter. Most of it, about 80%, has been already recovered. At the moment, the production is low because of an energy transition, but that may change depending on what happens in the winter. The production is exploited by a conglomerate that consists of a number of parties. The main one is the Dutch state. The practical work is being carried out by NAM, Nederlandse Aardoliemaatschappij, an oil and gas producing company, and Shell and Esso, or oil companies. Who receives the benefit? Well, most of all, the Dutch state. Over 70% goes into the treasurer's chest. It has been a massive boon to the Dutch economy. And in the beginning, the 1960s, it has mostly been spent on an expansion of the welfare state, building up the country after the disastrous effects of the Second World War. Later on, it's also been spent through special funds, for example, FES, and that has been, well, people could apply for projects, for example, in science and innovation. For example, at CWI, BRICS is an important project that has been used to hire tenure tracker staff at CWI, but also for infrastructure problems. And a recent example is a high-speed train network that connects Amsterdam via Rotterdam to Breda in the south of the Netherlands. However, there is also a downside to it. Depletion of the reservoir leads to a decrease in pore pressure. That in turn causes structural changes to the reservoir that's known as compaction, and compaction leads to subsidence. The ground drops. So that's one effect that's been noticed already for a longer time. A more recent effect is also earthquakes, because a drop in the pressure increases the stress on faults. They may slip and cause seismicity, which is noticeable through earthquakes. And of course, both subsidence and seismicity lead to damage to property, as is illustrated in the picture here. Many Groningen villages suffer from cracks in the walls that hold up the building. So you see all these kind of skeletons surrounding farms and houses in Groningen villages. That has led to a public outcry and changes in legislation. There was a major earthquake in Huizinge in 2012. And in 2014, the government put in place legislation to decrease exploration of the gas field. So what I'm going to talk about roughly in this talk today is first describe the data, then I'll give you a brief overview of a time series analysis where we look at the correlation between annual gas extraction protocols and the number of earthquakes in the same year. We're also going to allow spatial aspects to come in. So I'm going to talk about an exploratory analysis both in space and time. And finally, I'm going to use the results from this analysis to critique the standard model in this context, the rate and state model, and propose a modified rate and state model that may be used to predict earthquakes. So let us first look at the data. What do we have? Well, first of all, we need to know where the gas field actually is. So we need an outline of the gas field. And that's being maintained by TNO, a company in the Netherlands that works on projects for the government. They maintain shapefiles that can be found on the website over here. And you can see the outline here in the picture. Then we need the recorded earthquakes, and those are being maintained by the Dutch Met Office, KNMI. They record all earthquakes that happen within the Netherlands, both induced in Groningen, but also the natural earthquakes that happen more in the south of the Netherlands, which is kind of the outlying parts of the Ardennes and Eifel regions. So up to minor earthquakes also happen naturally in the south of the country. There is an issue of data quality. In the beginning of the exploration in Groningen, nobody thought that earthquakes were at all possible. and there was no extensive monitoring network in place, so a lot of these earthquakes were actually missed. They were also having rather low magnitude, so an earthquake is hard to distinguish from a heavy lorry passing by, and we need to set up a threshold. KNMI has looked, the Met Office has looked at what a suitable threshold is, and they came up with a magnitude of 1.5 that would be suitable from 1995 onwards. So that's the one we use. Since 1995, and in particular following the major housing event, the monitoring system has been expanded. So for recent years, a magnitude of 1.3 would suffice, but that would reduce the time period of which we have data. So we chose to work with the data from 1995 up to December 2021 with magnitudes of 1.5 and larger. And in the picture over here, you can see the spatial projection of all earthquakes and the temporal projection. So what you can see from the temporal projection is that the number of earthquakes is going up. First, it's quite steep. There are long periods in between earthquakes, and then it flattens off as earthquakes happen in quicker succession. Spatially talking, you see that most of the earthquakes happen in the central reservoir over here, with fewer earthquakes in the peripheral regions, and also somewhat lower numbers here in this area, which is known as the Haagstede block. In Groningen, production is being carried out by wells. There are a number of wells. There's one water injection well at Borgsweer that's indicated by the circle over here. Then there are production wells indicated by crosses in the picture, 29 of them. And there are observation wells indicated by the triangles in the picture, of which we have 22. Their location in Mercator projections are available through the site of the NAM, the production company, remember, one of the members of the conglomerate. And they have these plans for production in the upcoming period, in which they also give the coordinates of the wells. Not all of them have been in production for all the time. Some were taken out of production around 2010. They're also sometimes drilled in peripheral field, in particular the Haagstede area over here. And in the beginning period, when production was started up, small amounts were extracted from non-production wells, for example, the observation and the injection well. But these amounts are really negligible compared to actual production from producing wells, and none of it happened in the time period from 1995 onwards, in which we are interested. The patterns vary. For illustration, I've plotted time series of production at 3 wells. Amsweer, which is a fairly typical one. Eemskanaal in the middle, which is a very atypical one. And Tussenklappen, which is a well that on the whole follows the typical production patterns, but has been out of production for maintenance for a period of time, roughly between 2000 and 2010. Production values are available at several locations on the web. The NUM site has production values Also TNO, the analog side, has production values. They are differing somewhat because, well, these are monitored by Shell and they don't always inform the other parties that produce production values. So we wrote directly to Shell and obtained the source code by Mr. Rob van Ijs for each of the 29 production wells. Production started in 56, and you may remember that the field actually was discovered in 59, but previous to that time period, there were a number of small exploratory drillings going on in a nearby place called Ten Boer, but they didn't find much. So the production from 56 up to 59 is only at the Ten Boer location and very small amounts before the actual discovery of the main reservoir. Either way, we're only interested in the period from 1995 onwards. You can, why is Eemskanaal a special one? You see that if you look at the y-axis, that the amounts produced here are way smaller than the amounts produced in other wells. And another specific thing about the 13th pipe at the Eemskanaal site is that it's not actually drilled straight down into the earth, but actually it depletes the Harkstede block, which means that if we are going to look at production values spatially, we have to treat Eemskanaal 13 different from the other pipes at Eemskanaal that do drill straight down. And although the numbers here are smaller than those at other production wells, they're not that small that they can be ignored. The other data that we have is about pore pressure measurements in bar against time here for a number of wells. The typical one is Slochteren, which is given here by these filled discs. Harkstede is the main observation station in the Harkstede block, and that's separated off from the main reservoir by a large fault, which means that the pressure values here are somewhat larger, higher than in the main reservoir. Krongham is where originally the field was discovered, and they've been given by triangles. They're also quite close to the Harkstede block, and so their values also lie down a little bit. The Harkstede itself, but they're larger than the typical values in the reservoir as measured in Slochteren. And finally, there are also a couple of observations in Borsweer. And remember, Borsweer was the water injection well, so also their values are somewhat atypical. These value measurements are also available at the site of the exploration company NAM. In total, there are 2009 observations. The data does need some cleaning because sometimes these pressure measurements, they go wrong because, for example, it's been raining too hard and there's still some water standing in the pipes. And also for other reasons, sometimes there is maintenance being carried out in these pipes that interferes with the measurements. So this file does need some cleaning, and we're left with 2009 observations over the entire production period, and a smaller number when we restrict to 1995 up to 2021. So that brings me to our first statistical analysis, when we start looking at the time series of earthquakes against gas production. What you see in the figure over here as blue dots is the annual production in the Groningen field, cumulative over the entire field. What you see in red is the number of earthquakes that happened in every particular year with a magnitude of at least 1.5. The first thing to note is that the production values differ a little bit over the years. It dropped somewhat during the late 1990s. It started increasing again roughly up to the time of the Huizingen event, the major earthquake at Huizingen. After that, legislation came in to phase out production, so you already see a sharp decline. If you look at the number of earthquakes, there's two trends you can see. First of all, there seems to be a bit of a slope, so that the number of earthquakes increases with time, but there also seems to be a relation between production values and earthquakes. So after production was being phased out, you also see a drop in the number of earthquakes. And our goal in a statistical analysis is to quantify this correlation. So we need a model. Well, our data are counts. And a natural statistical model for counts is the Poisson distribution, which is depicted over here. If we have a rate parameter lambda that may depend on the year t, we have this expression for the Poisson probability of having n earthquakes in year t. E to the power minus the rate to the power n divided by n factorial. To quantify the effect of production, we need a formula for the rate in terms of production values. And because the intensity has to be a positive parameter as a rate, we work on the logarithmic scale and we assume a linear relation between log rate in terms of both time and the production in the previous year. So the production in the previous year here is indicated by C of t minus 1, and C tilde t minus 1 is the cumulative production counted from 1994 up to and including the year t minus 1. And this is a proxy for time because the cumulative amount increases, of course, in time. And it's from a physical perspective, it's way more natural to use cumulative production rather than the time trend that a statistician might perhaps prefer, because you don't expect the number of earthquakes to go on as time progresses when the reservoir has been depleted. Then we have these scalar multipliers, real valued alpha 1, alpha 2, and alpha 3. They are treated as the parameters in this model. They're unknown and have to be estimated, for example, by means of the maximum likelihood estimation method. We can do that, and we got values of minus 2.23 for the intercept, 0.025 for the parameter that quantifies the relation between the production values and the logarithmic rate of earthquakes, and a value of 0.64 for the temporal trend. We're of course particularly interested in the parameter that quantifies the effect of gas production. It is positive, which means that if we increase the gas production, also the seismicity rate increases, which is of course what you would expect. Is it statistically significant? Well, for that, we have to look at the confidence interval. For example, at a 95% level, we get a confidence interval that only contains positive values. And we conclude that indeed at level 95%, alpha 2 is significant. So there is a significant effect of gas production on the level of seismicity in the Groningen field. Pictorially, that's depicted in the figure over here. What you see here as black dots are the estimates for the intensity parameter in every year. And the gray dots are the limits of the confidence intervals for the annual earthquake rate parameter calculated by using asymptotics and the delta method. In particular, for the year 2021, we get an asymptotic confidence interval for the number of earthquakes that ranges from about 7 to about 14 earthquakes. And because 2021 has already passed, we can actually compare that to the actual number of earthquakes that happened, which was 12, which is indicated as the red point in the picture over here. Is the model any good? Well, we have to do a validation. Remember, we used a Poisson model in which the counts in different years were independent, and that can be that assumption can be assessed by looking at the residuals and the correlation. The residuals for seeing whether the Poisson model with the estimated rate is actually good. The autocorrelation function to see whether the independence assumption is reasonable. So what we've plotted here are Pearson residuals, which are raw residuals scaled by the standard deviation, and the estimated autocorrelation function. And you can see that the residuals are scattered around 0. Most of them are quite small. The range is from about -2 to 2.5 in the plus direction. The autocorrelation should lie around 1, and if independence is satisfied, that's what it does. To see whether these values are large or not, we've actually compared them to 19 simulations from the fitted model, which are indicated as envelopes by the black points over here. And you can see that for most of the legs, the empirical autocorrelation function, the red points lie in between the local envelopes. So all in all, the model fit seems to be reasonable, and we can conclude from here that indeed there is a positive association between gas production and seismicity. That's nice, but we've completely ignored the spatial aspects. So in the second part of my talk, I'm going to look at space-time models. The first thing we need to look at is the trend. So the rate parameter, if you like, the probability of finding an earthquake at a given place and time, is modeled, mathematically speaking, by the first order intensity function. And to estimate that, usually kernel estimators are used. In order to describe what a kernel estimator is, it's easier to work in one dimension rather than in 3 dimensions for space-time. So suppose we are looking at a real valued random variable of which we would like to estimate not the intensity but the density function in this case. So the black points over here indicate realization of the random variable. And you're probably all familiar with the histogram. So what does the histogram? It divides the values set in bins, in this case, the interval from -5 to +10. It divides it in these blue bins, and it simply counts how many observations fall within the bins and scales by the total number of observations. So in this first bin over here, we have 1 observation. The second bin has these 2 black points over here, so it's twice as high. Here there is 1 point. In the middle, there are no observations, so we have the value 0. And here again, these 2 bins at the right-hand side each have 1 observation, which we again scale by the total number of observations. Then that's nice, but it's also rather, bin. You can still see where each of the individual bins were located. And it would be nice to have a somewhat smoother representation. And that's what kernel estimation does. It replaces these bins by bell curves, the densities of a standard normal distribution, and places around each of the observed black points over here a bell curve. So a Gaussian with a given standard deviation. And then after doing that for each of the observations, it simply adds them up. And you obtain this blue line over here, which is actually giving a similar message as the histogram, namely that we have a bimodal density function. But it is a little bit smoother. In particular, this steep 0 is replaced by a valley rather than an actual 0. And visually, the rightmost picture here is more pleasing than the histogram. You can do the same idea in space, where you place 2-dimensional bell-shaped, curves, if you like, or filled curves around each of the points in a point process, in our case, the earthquakes. And you can do the same in space-time, where you also take into account the time at which an earthquake happens. And so you place 3-dimensional Gaussian kernels around each of the recorded location time combinations. Kernel estimates are sensitive to the choice of bandwidth. In space-time, you might also like to use a different bandwidth in space than in time, because a kilometer does not naturally scale to a second. Edge effects become necessary. In 1 dimension, you only have 2 edges, so some mass of these Gaussian kernels may leak out of the value set from -5 to +10. In space, that's more of a problem because there is more border to take into account. And in space-time, it becomes even more of a problem. So we have to look at edge correction. And the problem of a global bandwidth is also that it's sort of one size fits all. So in regions where there are many points, you would like to have a somewhat smaller bandwidth than in regions where there are very few points. Or in other words, if you use a one-size-fits-all, that's a kind of compromise between the dense and the more sparse regions. You tend to oversmooth in regions that are rich in points and undersmooth in regions where there aren't many points. So let's first formalize in mathematics what I've just said. So we have a point process psi in a spatial window WS, Cartesian product with a temporal window WT, so that lies in RD times R. There is an intensity function lambda, and we have different bandwidth in space and time, which we might represent by a matrix, a diagonal matrix of 3 by 3, which has HS as its first two diagonal entries and HT as its third diagonal entry. Then let kappa be a kernel, so a symmetric probability density function, for example, the Gaussian. We place this kernel around each of the observed points from the point process in a realization in WS times WT. We shift them to those points, and we scale by the bandwidth as represented by the matrix. And W here is an edge correction term. And if you pick that smartly, for example, using a local correction, which is simply the integral of the rescaled kernel with respect to the x point here, the point at which you try to estimate the intensity function. Then this is mass preserving in the sense that if you integrate out the estimated edge-corrected intensity function over the space-time domain, you obtain exactly the observed number of points in this space-time domain. In other words, there is no mass leaking away from your observation window, where mass now is the number of observed events, earthquakes in our case. Then the problem is, how are we going to estimate the bandwidth? And that can be done in several ways. Here we propose a non-parametric bandwidth selection based on the so-called Campbell-Mekker formula. What is the Campbell-Mekker formula? Well, you can show that the expectation of the sum over all the points in the process of 1 over the intensity function is actually the area of the window, where L here stands for a back measure. So this is the area of the window multiplied with the length of the time window. And that is nice, because then we can plug in an estimator for the intensity function with any bandwidth HS and HT, and compare that, the left-hand side, for this estimated intensity function to the right-hand side, which is a known quantity, the volume of the space-time observation window, which we know, and minimize the discrepancy over HS and HT. Now, if you have only one parameter, so for example, if you would work only in space, then usually there is a unique solution, though not always. If you if you minimize over two parameters, HS and HT, typically you will find a multiple solution, and we take the one that has minimal scale, so we minimize HS squared in 2 dimensions and HT for the time dimension. What is nice about this is that we don't need any knowledge about the process that generated the points. So in other words, we don't need any model assumptions, and this is a completely non-parametric technique. It's also computationally easy to do, where we have to note that the clearest maxima here are usually obtained if we temporarily ignore edge corrections in the estimated intensity parameter. And we're going to again plug in the edge correction once we have estimated the bandwidth. How can we compensate for global bandwidth smoothing and oversmoothing? The idea is due to Abramson. We may actually weigh the bandwidth by something that depends on the intensity of the points. And if the intensity of the points is small, we would like to have a large bandwidth. If the intensity of the points is large, we would like to have a smaller bandwidth. So one way of doing that is simply take a negative power of the intensity function. And the typical choice here is the negative of a half, and that is for asymptotic theoretical reasons. We can have neat Taylor expansions if we take this particular power. In practice, of course, you may take other powers. And then, well, plugging that into the kernel estimation idea gives us this expression for the Abramson adaptive kernel estimator. Instead of having hs squared times ht, we multiply them both by this constant that depends on the intensity. The same for the bandwidth matrix weighting. The diagonal entries of the H matrix are also scaled by the same constant in terms of the intensity function. However, this is sort of a vicious circle. We try to optimize a bandwidth based on an intensity function that we do not know. We need a bandwidth in order to estimate the intensity function. However, what you can do is a two-step procedure where first you use applying an estimator for the intensity, a provisional tentative estimator with a global bandwidth, and you plug that into the rating, the Abramson scaling factor, and find optimal adaptive bandwidth using again the Campbell-Mekker idea. If we do that for Groningen, we get a number of values. So the global bandwidth is about 9 kilometers in space and 182 days in time. And the adaptive bandwidth are somewhat differently, about 7 in space and 213 days in time. And the results are plotted in this picture over here. So what do you see? The left picture over here is the kernel estimator projected in space using a fixed global bandwidth. And the picture here in the middle is using the adaptive bandwidth. The ribbons here are the same. So what you can see is that the adaptive bandwidth emphasizes or puts a higher value to the central reservoir in the gas field. And that is because the bandwidth here, the scaled bandwidth is smaller in this region than in the far further away regions. There is also more blue here. So in these far away peripheral regions where there are very few earthquakes happening, it doesn't suffer from the oversmoothing in the fixed bandwidth, and you get actually the smaller values here in the periphery that are probably closer to the truth, although in the, for actual data we do not have a ground truth. You can see a similar phenomenon happening for the temporal projection. Here, the solid line is the adaptive estimator. The dotted line is the kernel estimator using a fixed global bandwidth. And you see that in the later period where earthquakes are more prevalent than in the earlier years, the peaks are higher in the adaptive estimator than for the fixed bandwidth. Our second goal is to look at interaction, and the counterpart in a point process framework of the autocorrelation function is the pair correlation function, which is defined as follows. We look at the probabilities of finding a pair of earthquakes, one in space location S1, time location T1, one in space location S2 and time location T2. And we divide that by the probabilities of finding earthquakes in S1, T1, multiplied with the probability of finding an earthquake in S2, T2. For pair correlation values 1 would happen when there is independence. There are no interactions between the points in the process. Values that are bigger than 1 indicate that the presence of a tremor at S1, T1 increases the likelihood of also finding a tremor at S2, T2. So this is indicative of a cluster behavior. And similarly, values smaller than 1 happen when the probability of both earthquakes happening simultaneously is smaller than the product of the individual probabilities of earthquakes happening. So that's indicative of a regular point pattern or an inhibitory point pattern. Now, if you were to estimate the pair correlation, we need a second order quantity, so we need 2 bandwidth. That tends to be unstable, and therefore often people look at cumulative statistics where we integrate the pair correlation function out over a cylinder in space-time. This is easier to estimate and way more stable. The similar interpretation holds if the inhomogeneous K function is larger than the volume of the cylinder. It's indicative of clustering because G is bigger than 1, so integration gives bigger values than the integral of 1. The same if K is smaller than the volume of the cylinder. This is indicative of regularity, and when there is no interaction formalized by a Poisson point process, the K function is equal to the volume of the domain. Of course, we can look at n tuples rather than pairs, so look for higher order interaction, and that leads us to 2 quantities: the empty space function, which formalizes how large the holes are in between clumps of points, and the nearest neighbor distance distribution, which quantifies the distance from a tremor to its nearest neighbor. For a Poisson point process, these are the same. Information about one point does not give information about where the other points are. So if we divide them out, we get a value of 1. For clustering, the nearest neighbor distances tend to be small and the voids in between clumps tend to be big. So that means that the empty space function is smaller than the nearest neighbor distance distribution function. And for regularity, the nearest neighbor tends to be relatively further away and the empty spaces tend to be smaller. So we have the reverse inequality. And here are the results for the Groningen gas field. We've plotted a projection over one line, R100R, of the K function and the empty space and nearest neighbor distance distribution function. And you can see, for example, in the left picture over here, that the scaled K function by taking the third root to get a straight line for the volume of the cylinder lies above this straight line. So we see a clustering. And similarly, if we look at the empty space function and the nearest neighbor distance distribution function, you can see that the empty space graph lies on top of the nearest neighbor distance distribution, which is again indicative of clustering. So the conclusion we can draw from these two graphs is that in the Groningen gas field, there is interaction going on between the points over and above what can be explained by trends. In order to build a model, we would like also to take into account the covariates that we have, and they are twofold. We have information about gas production, and we have information about the pore pressure in the pipes in clusters of wells. They play a different role. For the gas production, we have monthly observations for each of the producing wells, 29 of them, and we need these values over the entire space-time domain. So we need to smooth them out. And that can again be done by kernel estimation techniques very similar to what we had for the intensity service. We can again use a fixed bandwidth or an adaptive bandwidth, and we've chosen to use the adaptive bandwidth over here. What we get are values of 7.6 for the Pilot estimator and 6.9 for the Abramson bandwidth. We only look on the spatial projections per month because we have monthly values which we can simply take over this entire month. And here we can compare a typical January before the Huizinga event, for example, 2012, and the typical values after legislation came in to decrease the production values. And you can see that at the peak of gas extraction, there was way more gas extracted than in this case. The ribbons are the same. There is more red and yellow in this picture than there is over there. And it's also spread out over a larger regions. There's still a lot of production going on in the central part of the reservoir, as well as in the southwest and the southeastern corners. Whereas if you look in January 2021, most of the production in the central reservoir, where also most of the earthquakes happened, has been phased out, and the remaining production is mostly concentrated in the regions in the southwest and the southeast of the gas field. For the pore pressures, we have during the period of interest from 1995 till 2021, 352 measurements left, and there is measurement error going on here. So in order to extrapolate, we formulate a model where we have a mean and residual uncertainty. The mean is fitted by a polynomial in space and time, and for the noise field, we use white noise. And to see whether this model is actually reasonable, we plot the fitted values against the measured pore pressures and see whether they fall on a straight line. And we can see that although there are some deviations, for most of the values, actually the fit is not that bad. A straight line is clearly seen in the picture here. The residuals, we also plotted the histogram of them. You see that most residuals are close to zero, and the histogram is also rather symmetric around zero, so there are no systematic errors either to too large or too small values. And this is what the estimated pressure maps look like at the beginning of the time period of interest, 1995, and at the end of the time period, so at the end of 2021, the dawn of January 2022, January 1st, 2022. And the ribbons again are the same. So you can see that in the beginning of gas extraction, there is a constant value around 200 in the central reservoir. In the Haagstede Morg over here, the pressure is higher. And there are some higher values also in the periphery in the north eastern corners of the field. At the end of the period, because of the depletion of the reservoir, the pressure has dropped. So you see more blue, lower values throughout. Similar values in most of the reservoir, again somewhat elevated values in the Haagstede block and in the eastern periphery over here, and also a little bit in the peripheral field near Heinigerlee. And in the last 5 minutes of my talk, I'm going to discuss the state-of-the-art model that's used in seismology based on a differential equation that relates the intensity of earthquakes happening to a state variable gamma. That's the reason that it's called a rate state. The intensity is inversely proportional to the state, and the state satisfies a differential equation in terms of the pore pressure value x around here. You can rewrite this as a differential equation in terms of gamma, the state variable, with an exponent of the pore pressure values like this, and apply Euler discretization to get a difference equation where the state variable at location S and a time t plus the discretized delta value satisfies this equation over here. It's the previous value of the state variable plus the time, with an exponent in terms of the difference in pore pressure between time t plus delta and time t, and there are these parameters alpha and beta over here. The alpha is coming from a scalar multiplier in the differential equation, and beta a scalar between gamma and the difference in pore pressure values. Now, if x were to be constant in time, we reclaim the famous Omori-Utsu equation. What the people do is take the intensity and allow a Poisson process with that given intensity, estimate the parameters alpha and beta, and that's what we have. However, we saw before from the second order analysis that a Poisson point process cannot take into account interactions, but we do see some clustering. Another critique you could make is that the gas extraction is not at all taken into account. So we have to compensate for that somehow. And moreover, that the uncertainty in the pressure measurement is not taken into account, which also leads to biases in the rate state models. And typically, if you look at the predicted values, they tend to underestimate the number of earthquakes that actually will be happening. So in our ongoing work, we are proposing a modified rate state model that takes into account these critique points. So first of all, we assume that the pore pressures are a random field by explicitly also using the residuals and modeling them as a normal distribution with a given variance. We introduce gas production as a covariate in a linear model similar to what we did in the purely temporal, and we embed the whole in a Bayesian framework where we are going to do state estimation. So look at the posterior distribution of the state variable gamma of interest based on the actually observed earthquakes as given in the Met Office catalog. Okay, thank you for your attention. If you would like to know more details, here are 2 papers of ours that describe the work that I've presented over here. This is joint work with PhD student Jonas I. Baki at the University of Twente. For people from geology who may not know so much about spatial statistics, if you would like to know more about kernel estimation, K and J functions, interaction, plasma processes, etc., there is a textbook of mine, A Theory of Spatial Statistics, A Concise Introduction, published by CRC, Prestainer, and Francis, that you might like to consult. It's written for master students. There are example codes in R as well as some worked exercises too. Thank you again for having me. I think the organizers will have a Zoom link for questions. And of course, I would be happy to answer any you may have. Thank you. I will now stop the recording.
Thank you, Marie-Colette. Any questions from the audience? Yes.
First of all, thank you for your very interesting talk. I, however, have a question to the beginning. You did a test on the assumption of independence, which you then showed us to be true based on showing us that the correlation function is flat and does not exhibit correlation, but that could also, I think, be an effect of that over-dispersion you would see from the dependency in the point process, which you showed that is clustered in space, so it's probably also clustered in time. And so I wonder whether we would really like to encourage using independent tests on things that are obviously correlated in time.
I think the result is true. We did a bit more analysis of this also for the point process case, as you could see in the second part, and clearly there is interaction if you look at things on the detailed level of a spatial temporal point process. However, if you are going to look only for a given year, essentially you're looking at a union of modes of possible point processes, if you like, or processes with interaction. And there are theoretical results that state that if you look at unions of random point processes, in the limit you end up with a possible behavior. So if you superimpose lots of points, you're going to define away the interaction. And I think that's what's happening in accumulating things over years. Does that explain it? So you're right, there is interaction going on if you look at a detailed level, but if you aggregate a lot, basically summarizing the entire earthquake catalog in 27 numbers of counts in a given year, the aggregation is so big that you define away the interaction, so you can't see it in the year count.
Maybe another question? I have one, which is maybe a little bit off as compared to the main point you're making about the spatial-temporal point process, but I was intrigued by the way smoothing the production data, the filtering that you're using. I would expect in a real case study like that to have some flow simulation results or some hopefully more insights about what happens in the reservoir and trying to be a bit more, to input more physics, like if only anisotropy, maybe a well does not deplete completely isotropically, but maybe in an anisotropic fashion. So have you thought about that, and do you think that could be somehow integrated into your approach?
Probably, but it would need more expert knowledge about how this extraction is being propagated. And the only data we have is the production at well, so we just spread them out using Gaussian kernels. But of course, if you have information on the physics, you could build it in.
Okay. Well, I guess it's time is running, so thank you, thanks a lot, Marie-Colette, for a very interesting presentation.